In section 3.3, we're going to talk about increasing, decreasing functions and the first derivative test. The objective of this section, of course, is to find the extrema, that is the maximum or the minimum values of the function if they exist over an interval. Before we actually look at the first derivative test, however, let's talk about a couple of ideas here, that is increasing, decreasing functions. So first, definition of increasing function. We say a function is increasing on an interval I if for every x1, x2, so that when x1 is less than x2, f at x1 is going to be less than f at x2. And I have a graph to the right here. This is the graph that exhibits this definition. Typically with increasing functions, you would expect the graph to rise, as the name says, increasing. So it increases as you move from left to right along the x-axis. You have a comparable definition for decreasing function. A function is decreasing on an interval I if for every or for all x1, x2 inside of that interval, f at x1 is greater than f at x2 when x1 is less than x2. So for instance, if you take a look at now this drawing that I have here next to this definition, x1 lies to the left of x2, so x1, x2, the numbers on the x-axis increase, and as that happens, notice the function actually is decreasing as you go from left to right on the number line. And again, in general, you would expect a decreasing function to behave like that. You expect it to fall rather than to rise. Okay, and then our next definition is that of a monotone function. So we can call a function monotonic if it's either increasing or decreasing. Okay, so something like a sine wave, for instance, is not monotonic because it rises and falls. And I'm looking at over the entire domain here, from like here to here. If you segment it, if you restrict the domain, you can make it increasing or decreasing over a sub-interval, but we're talking about in general. If there are rise and falls on the graph, then the function is not monotone. Okay, next, in terms of increasing, decreasing, or being constant, we have our first theorem. This theorem says let f be a continuous function on a closed interval, differentiable on the open interval. Then one of these three things is true with regards to the derivative of the function at every point. So if the derivative f prime x is positive, remember that that is the slope of a tangent line. If the slope of a tangent line is positive for all x inside of that open interval, then the function must be increasing. Okay. And if the derivative is negative inside of that open interval for all x, then f is decreasing on the closed interval. And in part C, if f prime x is 0, then you have flat line. And of course, if it's flat line, that means the constant must be constant over the entire domain. Okay, so that's what those are. Now, our next theorem is actually the first derivative test. Again, we use the first derivative test for extrema of a function. And in this theorem, it goes as following. Let C be a critical number. Now, C is a number along the x-axis, and C is inside of this open interval from A to B. Okay, now critical numbers, remember, those are numbers, we defined those earlier. Critical number of a function these are the value or values of independent variable x at which the derivative is either 0 or does not exist. Okay, so C must be one of those numbers, one of those types of numbers, where the derivative either is 0 or doesn't exist. So if you have critical number of a continuous function f in an open interval, and suppose f is differentiable for all c inside of that open interval, except possibly at c itself, then one of these three things is true. In part A, if the sign of the derivative, that's what we're looking at, if f prime changes from positive to negative, Okay, so that is important. The derivative, in other words, changes sign from positive to negative. Now, positive to negative means the slope is positive and then it becomes negative. So a positive slope turns into a negative slope. So if that happens, and that transition happens at C, okay, then f at C must be a maximum, a relative max, or a local max, they call it. Okay, now if the sign of the derivative, the slope of a tangent, changes from negative to positive, so this time it's going down negative, and at C it transitions into being positive. At C, the transition is there at C. Therefore, the function must have a local minimum at C, or a relative minimum at C. Okay. Now, if the derivative is always positive or always negative, therefore the f at C is not an extrema. Okay, so there's no extremum. Remember, the extremum is the plural word. The singular word would be extrema. Extremum. That would be individual. That's one max or one min. Extrema would be the plural of that. This is singular form. So we're talking about a single value, f at C. That would be either a max or a minimum. In this case, it's neither. So if the derivative is always positive, the derivative always negative, therefore there is no extremum. And here are some visuals of these three situations. So in part A, something in the way of relative max, and then B with minimum, the relative min, and in part C we have no extrema. So we can see here in part A the function, again here the slope of a tangent is positive. The slope of a tangent transitions into negative at C. And notice here the definition set up here, C is a critical number and the function is differentiable everywhere except possibly at C. Okay, so if you look at in the case, the example I've made here, the derivative does not exist at C here. Okay, so just I made an example where it matches the definition. So at C, the slope of a tangent is undefined. However, it is a local max at that point because they're transitioned from positive to negative. And then we have a local min in part B. The transition is from slope negative, here slope's negative, transitions into positive, and of course that happens at C. Right here is where that transition takes place. Therefore you have a relative minimum at B. Part C is a case where there is no extrema. If you look at it, the slope of a tangent in this case is always negative. So coming from the left, slope's negative, then it becomes extremely negative, almost vertical here, right? A massive drop off, and then it continues being negative. Therefore, C is not where the extrema will occur here. So at f at C here, so if I call this, for example, this point is C, f at C. In this case, f at C is not an extrema. It means it's neither a max nor minimum. There is no extremum at that point. And then I have a couple of more examples. Now, again, in the case for part C here, I have f prime does not exist at C. In this case, it happens to be a vertical tangent. Again, f prime may not exist in part A at C either. So, be it it's a corner point, it's a cusp, or a vertical tangent. At all of those, the derivative does not exist. The derivative does not exist at corner points, cusps, and vertical tangents. Okay. Now, here I have a couple of more examples of local max, local min. The transition again, this time from positive to slope of a tangent being negative. So at C we have a local max. And local min transition from negative slope to a positive slope occurs at C. Therefore, f at c must be a local min. Again, remember at c here, because it's a cusp, therefore there is no derivative. The function is not differentiable at that point. Now here's a case where there's no extrema over the entire domain. Again, this function, the slope of a tangent, oops, sorry, that's fine. The slope of a tangent was negative coming from the, or I'm sorry, positive coming from the left. Then it transitions to 0, and then it picks up to be positive again. It continues being positive, right? So the critical number here at c is a critical number where f prime c is 0. And this point is not an extrema. It is not an extrema. Okay, means it's neither minimum nor maximum. So now let's take a look at some examples of this one. Okay, so in this example, we want to find the extrema of this function. That means we want to find the maximum or the minimum of the function if they exist. So before we can use the first derivative test, we need to find the critical numbers. So we are on our way to finding critical numbers. To find critical numbers, I have to find the derivative of the function, which I can use the product rule. That's going to be first times derivative of the second plus second times derivative of the first. And there you go, that is a derivative, right? Now, the need for simplifying the derivative is right in here. Remember, I mentioned that earlier in chapter 2, I believe, when we talked about finding derivatives and the importance of simplifying these derivatives, is because now we need to find critical numbers of this function, right? Therefore, that is f of x, critical numbers for the function. So we're going to set the derivative equal to 0 or c, the place where it's undefined. Well, the way this derivative looks right now, I need to simplify it so we can decide if there are points where the derivative is 0 or undefined. Okay, so I'm going to write, first one is negative x to 1/3. There's not much in that one. The second expression plus, I'm going to write this as 8 minus x divided by 3, and then x to 2/3. Okay. Okay, so let me clean this up again. This is going to be plus 8 minus x divided by 3, and then we're going to move x to 2/3 to the bottom. Okay, and then we need to combine these two now. The LCD, of course, is 3x to 2/3, right? So I'm going to multiply top bottom of the first fraction by x to 1/3. We're going to multiply top bottom by x to 2/3 so we can get the LCD, right? And these two multiply to just x, so the numerator is just going to be negative 3x, right? Because it's going to multiply top bottom by 3 also to get it to look like the denominator. Okay, and of course I have plus 8 minus x. And this, of course, again itself reduces to 8 minus 4x, and I can factor a 4. Therefore, the derivative is 4 times 2 minus x divided by 3x to 2/3. Okay, hopefully you follow that work. Now, the critical numbers are where the derivative either is 0 or undefined. Well, the only way a fraction can be 0 is if the numerator is 0. So we're going to set it equal to 0. And from this we get x is equal to 2. So there's this one critical number. And of course these critical numbers have to be in the domain of the function, right? Well, the domain of this function is going to be all real numbers. The domain of f is all real numbers, so 2 is fine. Now, place where the derivative does not exist, so here I'm going to say f prime does not exist when x to 2/3. The denominator of the derivative is 0, which means x is 0. So we have two critical numbers. The first one is when f prime of x is equal to 0. The second is when f prime does not exist. Now, to do first derivative test, I'm going to draw my number line here. Okay, and this is, we're looking at f prime now, the sign of f prime. The first derivative test looks at the sign of f prime for the critical numbers of the function. Okay, again, if you go back here, first derivative test, we're looking at C. These are critical numbers of f, not f prime, but f. And critical numbers of f are places where the derivative is 0 or undefined. Okay, so this is 0 and this one is 2. Now going back to the function, our function here, at 0. Okay, at 0, if I look at, for example, f at 0, the function does exist and it's 0. And f at 2 is going to be 2 to 1/3, 8 minus 2, right? Plugging in into the function, so that's 6 times cube root of 2. And 6 times cube root of 2 is about 7.6-ish. Okay. Now, let's take a look at the sign of the first derivative. Okay. We're going to pick a test point to the left of 0. So, for example, -1. Okay, a test point, and we're going to plug that into our derivative function. Okay. So that's going to be 4 times 2 minus -1 divided by 3 times -1 to 2/3. Now remember, -1 to 2/3, the denominator, that's just cube root of -1 quantity squared, which is positive, right? Positive. All we care about is the sign on the derivative, so not so much the number. So I don't need to reach for the calculator. So that is a positive number. And then if I look at the numerator, 2 double negative makes positive. So the numerator is positive, right? In this case, 12. 4 times 3, 12. But it is positive. So you have the ratio of positive over positive. Therefore, f prime is positive. You can pick a test point here like 1 and test it. You're going to see that when you plug in a 1 again into our f prime, means in here. Okay, let's plug in a 1 this time, a 1. So the denominator is going to be positive, and the numerator, 2 minus 1, 1, and 4, the product is 4. So that's interesting. It's going to be positive again. So notice the sign doesn't alternate necessarily, plus minus like that. So that's why I pick a test point, a safe bet of doing this correctly. And pick a test point beyond 2. I'm going to pick 3. So we have 4 times 2 minus 3. The numerator is negative. Denominator is 3, of course. 3 times cube root of 3 squared. That's positive. The ratio is negative. Okay. So these are our test points. Now, the positive symbol along the number line here, f prime positive, that means the function is increasing. And then 0 is critical number, so at that point the slope is 0. Actually, the derivative, remember, the derivative does not exist at 0. So something is happening there at that point. Most likely we have a vertical tangent. That's why, because the function is continuous, there is no asymptotes in there. So if the function is continuous, the derivative doesn't exist. We either have a corner point, we have a cusp, or we have a vertical tangent if there are no asymptotes. And then the negative here means this. So I'm going to write this. F prime is positive. F prime maintains its positive status. F prime negative. So because as you go from positive to positive, there is no transition. So at 0, there is no extremum. Okay. And now the transition from positive, we're looking at this segment. The transition from positive slope to negative slope happens at 2. So at 2, we're going to have a relative max or a local max. Okay, and the value of the local max is 7.6, almost 8 at that point. Okay, so again, we want to find the extrema of this function. The extrema, we're going to say that there is a maximum of the function. Max is 6 times cube root of 2 to be exact, and it occurs at x equals 2. And there you have it. There is the maximum. There is no minimum in this case because the derivative is going to be negative forever. So there is no transition from down to up slope. Therefore, there is no local minimum. Okay, so that's what it is. Now, of course, later on, we're going to graph these and see what the graph looks like. Let's take a look at another example here. We're done with that one. In this next example, we want to do the same thing. We want to find the extrema if they exist. X to 2/3 times x squared minus 8. It's a little bit more elaborate than the other one. Okay, so I'm just going to put the question, find the extrema. Oh, and the first derivative test, by the way, was right in here. That's where we did first derivative test. The way we determined L max, we used the first derivative test. And more specifically, we did first derivative test part A. We found the local max. So it was part A of first derivative test that helped us find that extrema. Okay, find the extrema means maximum and or the minimum. Remember, extrema is plural, means find all max and all minimum if they exist. So I need to find the derivative again before I use the first derivative test because we need to have critical numbers. So the first derivative, first times derivative of second plus derivative of first times the second. And there we have this one. Okay, now again we need to simplify this because we need to because we need to set it equal to 0 or see whether it's undefined at any point. Now again, remember, x to negative 1/3 is 1 over x to 1/3. So the LCD of these two expressions is going to be, your LCD is 3 times x to 1/3. That means I need to build my first fraction, which is 2x times x to 2/3 multiplied by 3x to 1/3 divide by 3x to 1/3. I'm building the fraction to the LCD, and the second expression is 2 times parentheses the binomial times divided by 3x to 1/3. You see, now they have the same denominators, which is good. Now I can combine them, 3x to 1/3. Now 2 times 3 in the numerator of the first fraction, 2 times 3 is 6. X to 2/3, x to 1/3 multiplies to just x, and then x in front of 2 makes it x squared. Plus the latter one is 2x squared minus 16. And we have a couple of like terms. The x squared are like terms, makes it 8x squared. We factor 8 at the same time. And there we have, this is simplified. That's again the importance of having derivative in simplest form. Now, f prime x equals 0. We're doing CNs. CN means critical numbers. And we need to find where f prime does not exist. In a fraction, f prime does not exist when the denominator is 0, means x to 1/3 is 0, therefore x 0. F prime x equals 0, again in a fraction, it can be 0 only if the numerator is 0. So here we have x squared is 2, and x will be plus or minus square root of 2. And there you have it. So there are 3 3 critical numbers of this one. And again, the domain of this function, the original function, is going to be all real numbers, because you have cube root, that's a polynomial. No problem. Domain is all real numbers. Domain of f, let me just put that on the side. Domain of the function is negative infinity to infinity, because sometimes we get critical numbers that are not in the domain of the function. We simply discard or toss those out. Now we are about to do our first derivative test, but we are not doing that yet. This is f prime. This is simply a number line. So it happens 0 is a critical number, so 0 is that. Let's see. Let's do f at 0. F at 0, the original function. That's going to be 0 to 2/3, 0 squared minus 8. 0 to 2/3 times 0 squared minus 8. The upfront is 0 times anything is 0. So f at 0 is 0. And then we have a square root of 2 here. That's root 2, and this is negative root 2. And let me see here. It looks like this is, an even function. So it's going to be symmetric with respect to the y-axis. Okay. The plus minus root 2 kind of tells me that. Anyway, we use that information, odd evenness of a function, when we go to graph these functions in another section. Okay, let's take a look at the test points now. So I need the test point here, here, as well as here. So beyond square root of 2, I'm going to pick 3, for example. You can pick 2, you can pick anything. Remember, square root of 2 is about 1.4, so anything above 1.4 would do. And we are plugging it into f prime. This is f prime now. This is where it's being plugged into, at 3. So that's going to be 8 times 3 squared minus 2 divided by 3 times 3 to 1/3. Well, the denominator is positive. Remember, don't reach for calculator. We don't care about the number itself. We only care about the sign. The first derivative test only look at the sign of the derivative, first derivative. So we only need the sign out of this work. 3 squared is 9 minus 2, 7 by 8, 56. That's positive. So beyond root 2, the slope of a tangent is positive, means the function is increasing function, right? Between 0 and root 2, I'm going to choose 1. And again, we're going to plug it in. That's going to be 8 times 1 squared minus 2 divided by 3 times 1 to 1/3. So this is going to be a positive denominator. The numerator now becomes negative, because 1 squared is 1. 1 minus 2 is negative. 1 times 8 negative. Numerator negative divided by positive denominator makes that negative. The function is decreasing. Okay, so f prime is negative. And let's choose negative 1. Another test point, negative 1 squared minus 2 divided by 3 times negative 1 to 1/3. And this time the denominator, cube root of negative 1, is negative. In the numerator we have negative 1 squared 1 minus 2, negative 1 by 8 negative. The ratio is positive. And there we go. So it looks like this one is alternating signs, right? If you pick negative 2, again a quick cursor check, negative 2, 8 times negative 2 squared minus 2, that's going to be positive, right? Because negative 2 squared 4 minus 2 is positive. The denominator is going to be negative, right? Because you have 3 times negative 2 to 1/3, which is cube root of negative 2, that's negative. The ratio will be negative. So you have negative, negative, negative. So coming from the left, the function decreasing, slope positive means increasing. Now we are about to do first derivative test right now. The place where the transition happens from decreasing, this f prime is negative, right? Here f prime is negative, and transition to f prime positive. So this has got to be a local min, an L min here, a relative minimum. Transition from positive to negative at 0. So at this point we have a local max. Okay, this is an L max. This is f prime negative. And then finally f prime less than 0. And then at square root of 2, the transition is from negative derivative to a positive derivative, f prime positive. So this is going to be at square root of 2. At this point we're going to have a local min, an L min here. Okay, perfect. So it's got some action going on in here, right? We're going to have local max, and then we're going to have local min. So these are the extrema now. A local max is at 0, f at 0. So it's going to be 0 at x equals 0. The max is 0, happens to be 0, same as the critical number. The local min, we have two of those, right? The local min is going to be f, I didn't do f at square root of 2, f at root 2. And this is going to be, we're going to plug that into our function. Remember, it was x to 2/3 times square root of 2x squared minus 8, whatever that turns out to be. And let's see, let me simplify this one. It's not too bad to simplify. So square root of 2 to 2/3, that's root 2 squared, right, to 1/3. Square root of 2 squared, that's just 2 minus 8. Square root of 2 squared first, that's 2 to 1/3 times negative 6. Okay, and then 2 to 1/3 times negative 6. That's going to be about negative 7.3. I think we did that earlier, right? Go back up here. Yeah, cube root of 2 times 6 is 7.6. It just so happened we have that up there too. Okay, 7.6. Negative 7.6. That's what that is. So that's the value of L min, and that's going to be at x equals square root of 2. There's a second local min. It's negative 7. Local min is going to be again negative 6 times cube root of 2 at x equals root 2, and there you go, I put those together at root plus minus root 2. So we have local mins 2 that happen to be the same. Okay, they're local to an interval, open interval. And that's what we wanted to do in this segment. Now, in our next segment, we're going to do some exercises from your book now. Okay, so I went ahead and copy pasted these problems from your textbook into this page, and let's take a look at, for example, we're going to look at number 16 in that bunch. They're all polynomial functions, so let's do one from that segment. And then next to that, let's do a rational expression. Let's do a couple of those. And let's see, let's take a look at number 30, something like that with radicals, and then going down some trig functions. How about we'll look at 36. Okay, so those are the ones we're going to look at now. And that's all we want to do in this section, these types of exercises. So in exercises that we're looking at, the question reads part A, find intervals on which f is increasing or decreasing. And B, find a relative or local maxima and relative minima. It means all maximum and all minimums. Okay, that's what those are. Okay, so first we need to determine whether the function is increasing, decreasing, or what interval. So exercise number 16 here, the function f of x is equal to negative x to the fourth plus 2x squared plus 1. Okay, therefore, before we do anything, we need to take the first derivative. Because remember, in this section, we started by defining, let me go back up here. We defined what we mean by increasing, decreasing function before we looked at the first derivative test, right? And right in here, this is what we want to establish. Over the interval in which the function is increasing and the function is decreasing. Okay, now what we're going to do is we're going to use the sign chart on the first derivative to determine that also. It makes it really easy. Okay, the derivative, almost trivial, plus 4x. Now, domain of this function, domain is all real numbers. So I always check the domain just to make sure the critical numbers are good inside of the domain. Because it doesn't make sense to have a critical number where there is no function at all. We're not talking about any function if it doesn't exist. Now, the derivative itself is a polynomial function, and the derivative of, polynomial functions are differentiable everywhere. So there is no place, in other words, there is no point at which f prime is undefined. So the only critical number is f prime x equal to 0. So I'm just going to set this equal to 0, factor the 4x, and I get 1 minus x squared equals 0, right? And or you can factor negative 4x, it doesn't matter. Now, from this we get x is 0, or 1 minus x squared is 0, which means x is plus minus 1, right? Move x squared to the other side, take square root of both sides. So we have 3 critical numbers for this exercise. Now we're looking at, let me move this a bit lower. We're looking at f prime now, not f, but f prime. Okay, and this function is continuous everywhere. Okay, that is the derivative. The derivative is continuous everywhere. Now, here's 0, 1, and this is negative 1 on the number line. If we pick a test point, like, for example, negative 5, it doesn't matter, and plug it into your derivative, okay, here and here. Okay, when we plug it negative 5 in there, or negative 2, whatever negative, doesn't matter. So negative 4x cubed, this is going to be negative, right? You can plug it into it and see. The x cubed part of it will be negative, and the negative in front makes it positive. Plus the 4x part, when x is negative 5, that's going to be negative, right? Oh, let me actually do this a better way. We look at the factored form. Okay, let's look at the factored form of f prime, this version of it. Okay, I'm looking at the factored form of it. So I'm plugging in negative 5. Let me actually show you the steps here. So I'm doing 4 times negative 5 and 1 minus negative 5 squared. There we go. Well, this is negative. Negative 5 squared is 25. Positive 1 minus 25, that's negative. Negative times negative is positive. Okay, positive. So that means the slope of a tangent is positive. Between negative 1 and 0, choose negative 1/2 and plug it into the derivative. So it's going to be 4 times negative 1/2 times 1 minus negative 1/2 squared. Again, this is negative. Negative 1/2 squared is 1/4. 1 minus 1/4, right? 1 minus 1/4 is positive. Negative times positive is a negative. That means the derivative negative means the slope of a tangent is negative. Okay. Choose 1/2. Our test point, 1/2. So it's 4 times a half. 1 minus 1/2 squared. 4 times a half, that's 2. That's positive. A half squared 1/4 again. 1 minus that, positive. Positive times positive is positive. So the function is now positive, increasing, because the derivative is positive, so the function must be increasing. And let me erase these. And then next I'm going to choose a test point like 2, 3, whichever you like. I'm going to pick 3. So it's 4 times 3, 1 minus 3 squared. This is positive. 1 minus 3 squared negative, the product will be negative. So the derivative is going to be always negative beyond that. So this is how we actually partition the number line into positive and negative segments with those test points. Now that I have that all cleaned up, place where there's a transition from positive to negative, this is going to be a local max. Here there's going to be a local min. Transition from negative to positive, and again positive to negative is local max in this one. Okay, now to answer the question, increasing. The function is increasing over the interval from negative infinity to -1. And also increasing from 0 to 1. Okay. Now, the function is decreasing. It's going to be decreasing from -1 to 0 and from 1 to infinity. Now, a note about these intervals, by the way. Some calculus textbooks, they include at the transition point, like at -1, where the function reaches here. Well, which is it? Is it positive or negative? Well, remember at that point the derivative is 0. So the function is neither increasing nor decreasing. But so some textbooks, don't be surprised, they do this. They actually include the endpoints because they're thinking about an interval. So this is how they will report it. Of course, infinity is always parentheses, plus minus, because we don't know what those are. Again, some calculus textbooks use brackets at transition points where the slope is 0, and others do not. I'm not picky, whichever is fine. I tend to go myself with parentheses. I don't include those. Okay, so I'm just going to erase these, but I just want to mention it that some textbooks, don't be surprised, like you look at the answer in the back of the book and they have brackets, and that is why. I'm going to stay with parentheses. Okay, now that answers the first part. The first part, part A, says intervals on which function is increasing, decreasing, and then part B says actually find the relative extrema. Okay, so this is part A we just did. In part B, we can now answer part B easily. The local max, that's our first extremum. Actually, there's 2 extrema, right? There are 2 local maxes. So the local max occurs at -1 is f at -1. The other is f at 1. See, there's 2 extrema. They could be the same or they could be different. The local min, there's only one local min. It's going to be f at 0. Remember, these extrema are the values of the function, the y values, in other words. So I'm going to plug into -1 into our function. It was negative of x to the 4th plus 2x squared plus 1. And f at 1 would be negative of 1 to the 4th plus 2 times 1 squared plus 1. So negative of 1 to the 4th power, this one is negative 1. Remember how this works. This is a little tricky. Negative 1 to the 4th means negative of 1 to the 4th, which is negative 1, because 1 to the 4th is 1. And negative 1 in parentheses to the 4th is 1. So be careful. I'm going with this version of it. So that's going to be negative 1, and this is 1. They add to 0. Therefore, f at 1 is 2. Now, f at negative 1 will also be the same. So the local max is 2, occurs at 2 points, 1, negative 1. The local min is f at 0. That's you put 0 in for x. 0 and 2 times 0 squared plus 1, that's 1. So L min is 1. It occurs at 0. These are the local extremas. You see that? In the x values are where you find them, where they actually occur. All right, and we're done with that exercise. Pretty straightforward, I think. The other ones, these are all polynomials, so they're all done the same way. Let's take a look at number 24. In number 24, x over x squared plus 1. X divided by x squared plus 1. Okay, so that is our function. Let's find the derivative. F prime of x is, we can use the quotient rule. You square the denominator, and then repeat the denominator times the derivative of the numerator, which is 1, minus numerator times derivative of the denominator, this denominator, not the second one, times 2x. Okay, and this is going to be x squared and negative 2x squared. That's negative x squared, and 1 distributes, so I have 1 minus x squared divided by 1 plus x squared squared. Oh, the function, by the way, up here, they mentioned the domain. Yeah, all real numbers. Okay, let's take a look at domain of this function. The domain of this function is going to be, again, all real numbers. There's no way the denominator can be 0, right? Because you square the x. Positive, negative, it's going to be positive. At 0, it's going to be 0, but then 0 plus 1 is 1. So the denominator is never 0. So the domain of the function is all real numbers. Now, look at the derivative function here. We need to find the critical numbers, Cn, critical numbers. Places where f prime of x is 0, and places where f prime does not exist. Now, in a fraction, this is f prime. F prime doesn't exist if the denominator is 0, but then 1 plus x squared cannot be 0. So in other words, the derivative always exists here. The domain of the derivative is also all real numbers. Now, f prime x equals 0, that means only the numerator can be 0 to make the fraction 0. That means x squared is 1, so x is plus or minus 1. So we have 2 critical numbers for this exercise. I'm going to draw the number line. This is f prime, and again, f prime is continuous everywhere in this one. My reference points are 1, negative 1. 0 is just a number line here in the middle. Now, choosing test points. Let's see. Below negative 1 and the derivative, remember, we're plugging into this. We're plugging into 1 minus x squared over 1 plus x squared squared. So I'm choosing negative 2, okay, for my test point. Negative 2. It's going to be 1 minus negative 2 squared. That's 1 minus x squared. And the denominator, I don't really need to substitute. Let me do ones, but I won't the other ones. Negative 2 squared plus 1 squared. See, because the denominator is positive, isn't it? This, we just said it can't be 0. It's always positive, you square it. So denominator, because of the squaring here, is always positive. So just test point in the numerator. Negative 2 squared is 4. 1 minus 4 is negative 3 negative. So function is decreasing. Slope of a tangent is negative. F prime negative. Between negative 1 and 1, remember there's only two critical numbers here, negative 1 and 1. This is just my reference point on the number line, 0. So pick 0 actually. Let's do 0. My test point is 0. So I get 1 minus a 0 squared over denominator is always positive. So that's positive over positive. It's going to be positive. And then choose like 2, another test point here. Denominator is always positive. I won't even bother with that, right? In the numerator, I have 1 minus 2 squared. That's negative over positive, which makes negative. So the function again is decreasing. Here the function increasing. And we are good with this one. Now, let's see. The transition points from negative to positive slope, there f prime is positive and f prime is negative. There's going to be a local min here and a local max or relative max up there. Good. And the determination of L min, L max, by the way, that's when first derivative test kicks in. So we just did the first derivative test by calling these L max, L min. So let's answer part A. The function is increasing, or you see plus signs between negative 1 and 1. It is decreasing, where the sign, you have negative signs, from negative infinity to negative 1 and from 1 to infinity. Okay. In part B, the question says find the extrema. The local min is going to be equal to f at negative 1. And f at negative 1, you put negative 1 over negative 1 squared plus 1. You go to the function itself. That's negative 1/2. The local max is going to be f at 1. That's going to be, again, f at 1 is going to be 1 divided by 1 squared plus 1. That's 1/2. Okay. So those are the local min, local max. Remember, those are the values of the functions. And that's what we did. Okay, so hopefully you're okay with number 24. Let's take a look at number 26. This one. X squared negative 3x plus 2 over x squared plus 2x plus 1. I'll try to memorize that. In number 26, it was f of x equals x squared negative 3x plus 2. The other one was x squared plus 2x plus 1. Okay, let's find f prime of x, our derivative. Okay, now let's see if this is factorable. These may be factorable. Okay. X squared plus 2x plus 1, that is x plus 1 squared. That's good. The numerator is x minus 2 times x minus 1, isn't it? Okay, so those happen to be factorable. Okay, let's take a derivative now. So I'm going to use the factored form of the denominator, okay? So it's going to be x plus 1 to the 4th power, right? Remember, for derivative, you square the denominator. That's going to be x plus 1 to the 4th. Now, and then we repeat the denominator, which is x plus 1 squared, times derivative of the numerator, which is 2x minus 3, plus the numerator, x squared negative 3x plus 2, times the derivative of the denominator, this, which is going to be 2 times x plus 1. And of course, chain rule, derivative of inside is derivative of x is 1. Okay, now let's see. Before we actually distribute combine like terms, I see the x plus 1 in the numerator as a GCF here and here. Let's factor x plus 1. Okay. From the entire first expression, because there are two factors of x plus 1, one of them is being factored out. So that means I still have x plus 1 times 2x minus 3 plus removing GCF from the second expression, which is from this. Removing x plus 1, I just have 2 now, right? On the outside, and I'm going to distribute to the inside. So that makes it 2x squared negative 6x plus 4 divided by x plus 1 to the 4th. Okay, we can divide out one of the x plus 1s, and in the numerator I'm going to FOIL and combine like terms. The first two binomials, it's 2x squared negative 3x plus 2x minus 3 plus 2x squared negative 6x plus 4 divided by x plus 1 cubed. So again, we're getting into expressions whose algebra is a little bit long, not difficult, but it's just, I call them tedious. Okay, let's see if we did this right. So I got 2x squared, x squared minus 3, yeah, I'm just double checking, that's 2x squared negative 3x plus 2x minus 3. Yeah, we can combine like terms now. Okay, so let me make sure again everything looks good. Yeah, that's fine. I distributed, factored, and I did the quotient rule. Oh, actually, I'm sure some of you were screaming about this one, right? That's a negative because of the quotient rule. Sorry about that. So that's actually going to make this negative, that's positive, and the 4 will be negative. Other than that, let's see. I did the FOIL right, and then, so this is of course going to be negative 2x squared plus 6x, and then minus 4. Okay. So we have a couple of opposites, 6x, 2x, 8 minus 3, that's 5x, and minus 7. Okay, x plus 1 cubed, and just gonna make that shrink to fit. There we go, there's my fraction line. All right, I think everything looks good now. So now let's find the critical numbers of our first derivatives. So we're doing the CNs now. Places where f prime of x is 0 or f prime does not exist. Remember the backward e, that's the existence modifier. Now again, we set the numerator equal to 0, we get x is 7/5. That's one critical number. Place where denominator does not exist, those are the zeros of the denominator. Aha. So at -1, we either have a cusp corner point or a vertical tangent. Later on, we'll actually look at those more closely when we graph the line. At this point, we just want the critical numbers. And once we have the critical numbers, this is f prime. And again, this function is continuous everywhere. The derivative is continuous everywhere except at -1. The derivative does not exist. Now looking at the domain of this function, by the way, the domain of the function, it's a rational expression. So the domain is all real numbers but zeros of the denominator. X cannot be -1. So notice, to begin with, -1 is not in the domain, so this critical number is no good, right? It's not in the domain. Let me just write that, not in domain of f. So we shouldn't even count that, right? It's not in the domain. But here we go. Here's a 0. This is -1, which the graph at that point, let's say, the function does not exist. So there is no graph if we graph this. And 7/5, call this 7/5 is 1 3/5. Okay. And let's see our test points. I'm gonna pick, and our function, remember the function was, this is our function. Okay. And I'm looking at the factored form. Okay. I'm looking at this one. X minus 2, x minus 1, x plus 1 squared. And x plus 1 squared. This is where I'm going to substitute my test points into that. So let's pick a -2. My test point, -2. First factor is going to be -2 minus 2, negative, times -2 minus 1, negative, divide by -2 minus 1. Oh, again, we are in a situation, denominator is always positive, right? So don't plug into the denominator, just make that positive every time. So we have positive by positive, so that's going to be positive. Function increasing. Between -1 and 7/5, I'm going to pick 0. 0 minus 2, negative. 0 minus 1, negative, over positive. So that's going to be what? Negative times negative is positive over positive. That's going to be positive again, right? Let's see. 0. Make sure I plugged it in correctly. So I get negative, that's positive over positive. Yeah, it's got to be positive. And then beyond 7/5, you could have also plugged in a 1. The 1 we get 0 actually. Oh, hold on just a second here. Let me see. At 0, at 1, the function is 0. Okay, hold on. Okay, I see. I did something wrong here, folks. Let me correct this. We're looking at f prime. I didn't copy my f prime correctly. Hold on. So let me erase this part for now. Okay, because I'm plugging into here, but that's f, not f prime. Sorry, f prime is this one. So we're putting our test point into there. Let me try again. So -2 into f prime. So that's 5 times -2 minus 7. And now it's better. -2 plus 1 cubed. The denominator is negative. The numerator, -10, -7. Negative times negative divided by negative is positive. Okay, that one looks good. Let me try 0 for my test point. That's 5 times 0 minus 7. Numerator is negative. In the denominator, I have 0 plus 1 cubed, which is positive. The ratio is negative there. And finally, beyond 7/5, choose 2. Okay, 5 times 2, 10 minus 7. Positive numerator. I'm looking at this expression. And 2 plus 1 is 3 cubed, positive. Positive over positive is positive there. So please verify those. Now it looks good. Function is decreasing, function is increasing. So here again, we're going to have a local min, transition from negative to positive slope, transition from positive to negative slope is going to be a local or relative max. So we're good on this one. Oh, actually, I'm so sorry. It's so easy to fall into this trap. Remember, at -1, the function does not exist, right? At -1, f does not exist. So it wouldn't make sense to say I have L max, even though it looks like transition. But remember, -1 is not in the domain of the function. There is nothing there at that point. So the first derivative test set provided the critical numbers of that function, they have to actually be in the domain of the function. But anyway, so that's for the reason that's not going to be a local max, because -1 is not in the domain of the function at all. So we just ignore that. However, at 7/5 we have a local min, and the local min is going to be f at 7/5. And for this one now, f at 7/5, this is where I'm actually going to look at the original function, what I was doing earlier. It's going to be x, maybe I'll go to the original, maybe easier to plug into that one rather than to the other one. Yeah, let me do that. So it's going to be 7/5 squared -3 times 7/5 plus 2, and then divided by 7/5 squared plus 2 times 7/5 plus 1. Okay, and let's see, that's going to be 49/25 negative 21/5 plus 2. I'll show you a quick way to do this in a moment. This is 49/25 plus 14/5 plus 1. The reason I'm writing 2 and 1 like this, I'm going to multiply top bottom by 25. Okay. Multiply, oops, sorry about that. Multiply top bottom by 25. And let's see, when I distribute 25 times 49/25, that's just 49 minus 21 plus 50 all over 49 plus 14 plus 1. See, the fractions go away. So that's going to be 28, 50, 78 over 50, 64th. Okay. And let's see, make sure I did this one right. I see, hold on. I'm sure some of you can say, no, you didn't do that right. Okay, I'm going to distribute here. The first one is good. Second one, I get 25 times 21 by 5 is 25 by 5 is 5 times 20 is 105. It's 105. There you go. Plus 25 times 2 is 50. In the denominator, 25 times 49/25, 25 divided by 5, 5 times 14 is 70 plus 25. That's better now. Okay, so the numerator is going to be, let's see, in the denominator I'm going to have, let me do this and I'll just put the answer for you. Okay, so that's what it amounts to. Now I can simplify this, of course. 144 is divisible by 6, so it's going to be 1 times, I believe it's 24. There you go, -1/24. That's the value of the local minimum, and it occurs at 7/5. Okay, let's take a look at, let's see, which one we're going to do next. Okay, we're going to do number 30 next. Okay, in exercise number 30, here we have f of x is equal to x divided by square root of x squared minus 1. Now first, domain. Okay, the domain of this function is going to be for a fraction. We got to look at places where denominator is 0. The numerator is defined everywhere. Denominator, however, we have two things in the denominator. It cannot be 0. X squared minus 1 can't be 0 because we have division by 0. So there you go. Right away, plus minus 1 is out. Also, the implied domain of the square root, x squared minus 1, has to be positive, which means x minus 1 times x plus 1 has to be positive, right? Again, that is what we call the implied domain of the square root. Now, to decide the domain, this is -1, here is 1. Pick a test point such as 0. 0 minus 1 is -1. 0 plus 1 is 1. The sign is negative. I'm looking at the sign of the product. Okay. Pick a test point here like 2. 2 minus 1 is 1. 2 plus 1 is 3. It's positive. And this should be positive. Okay. Now, we want products that are positive in order to qualify in the domain, right? So that means here and here, the domain finally is going to be -infinity to -1 parentheses, union 1 to infinity. This is the function now, not the derivative, that's just f. We determine the domain. So remember, there is nothing between -1 and 1. So if we have a critical number that is -1 or 1 or anything in between, we're just going to ignore the first derivative at that point. Okay. Now let's actually do our first derivative. F prime of x here is. And I'm going to, let's see, here's what we could do. No, that's fine. I was thinking of doing the product rule. This is what I'm thinking. F of x is x times x squared minus 1 to -1/2. You can think of a function as that and use the product rule. If not, we can use just a straight quotient rule. Let's do the quotient rule. The thing with product rule, if you do that, then you're going to end up getting LCDs and combine like terms and combine two fractions, things like that. Whereas quotient rule, it's already in the LCD form, so to say. Okay, square the denominator, x squared minus 1 squared. Repeat the denominator times derivative of the numerator minus numerator times derivative of the square root. Derivative of x squared minus 1. That's x squared minus 1 to 1/2 derivative of that. So it's going to be 1/2 x squared minus 1 to -1/2 times 2x, right? Chain rule. The 2's come out. So it's going to be x over square root of x squared minus 1. And there we have that one. That's the derivative of the denominator. Now, let's clean up this thing. I'm going to multiply top bottom by square root of x squared minus 1. Because I see a fraction here, that's why we want to get rid of the complex fraction. Now, multiply top bottom. I'm going to write it. Multiply top and bottom by square root of x squared minus 1. Therefore, f prime of x becomes, well, multiply square root of x squared minus 1 times that. We're just going to get in the numerator. It's just going to be x squared minus 1 minus x squared, because when you multiply it times top, the square roots cross out. Okay. And when we multiply the denominator by it, we're going to get square root of x squared minus 1 cubed. There's already 2 there. We multiply by 1 more, makes it 3. Perfect. And then we can actually work this one. We have a couple of opposites. So this is just going to be -1 over x squared minus 1 to 3/2. Okay, that's what that turns out to be. Now, let's do our decreasing, increasing. So I need to draw my f prime. Oh, critical numbers, right? We didn't find it. F prime x equals 0. Well, this derivative cannot be 0 because the numerator is always -1, and only in a fraction can be 0 if the numerator is 0. Well, the numerator is -1, so it's never 0. So no critical numbers emerge from that expression. What about f prime not existing? That's place where denominator is 0. That means x squared minus 1 must be 0, or x is plus or minus 1, right? Now, interesting, because remember the domain of this function, the domain, we said x cannot equal to plus minus 1. That's when you get division by 0 in the function. So interesting. I'm just going to say this one is not in the domain of f. So there are no critical numbers in this one. So that means there's no extrema, because remember Fermat's rule, if the extrema exists, they have to occur at critical numbers. But let's see what's going on with this one a little bit more. So we know the answer, no extrema. Again, remember at these points the function does not exist, right? And the domain of the function was everything less than -1, everything above 1. Okay. Now, if I just want to look at the sign of the derivative, because we still need to answer increasing, decreasing over which intervals. So at test point -2, and we're looking at the derivative, right? We're looking at this function. -1 divided by -2 squared is 4 minus 1 to 3/2. That's 3, so it's negative over positive or negative. There is nothing here, right? So don't pick a test point there. The function does not exist, right? That's not part of the domain. And you can see that also, by the way, from the derivative also, right in here, that it doesn't exist. Nothing there exists. And beyond 1, let me choose 2. Again, the numerator is -1, denominator 2 squared, 4 plus 1, 3. That's positive, right? So I have negative over positive, that's going to be negative. So this function is always decreasing, right? Negative, that means the slope of a tangent. F prime is negative. F prime is negative. Later in another section, it's interesting. We'll see the graph of these and just gives us more information as to what's going on with the function. Okay, but for now, in part A, again, the answer to increasing, we're going to say f of x is increasing. Well, is it ever increasing? None. It's not increasing. F of x is decreasing. So where is it decreasing? From -infinity to -1, union 1 to infinity. So this function is always decreasing. And there is no extrema, part B. There is no extrema, because there is no transition from, let's say, negative to positive or from positive to negative. So we don't have that. And therefore, there are no extrema for this exercise. Okay. And that's all in number 30. Let's look at one last one in this section and we wrap it up. So let's take a look at exercise number 36, a trig function. Sine x over 1 plus sine squared x from 0 to 2 pi, endpoints not included in number 36. So exercise number 6, again we have f of x is equal to sine x divided by 1 plus 1 plus sine squared x over the interval from 0 to pi. Okay, we need to find the derivative first of all. F prime of x is. So we're going to use the quotient rule in this one again, right? f prime of x is, you square the denominator, 1 plus sine squared x squared. Repeat the denominator, you square the denominator, repeat the denominator times derivative of the numerator, which is derivative of sine is cosine, minus the numerator times derivative of the denominator, derivative of sine squared, derivative of 1 is 0, derivative of sine squared is going to be 2 sine x, and then chain rule, derivative of sine is cosine x. Okay, and we can simplify this one, 1 plus sine squared x squared. Now in the numerator, let's see, so we're gonna get, I see cosine x, let's factor the cosine x. From the numerator we get 1 plus sine squared x from that expression, and then from this expression we get negative 2 sine squared x, right? Cosine is factored. Now we have a couple of like terms in parentheses in the numerator, that's 1 minus sine squared x over 1 plus sine squared x squared. Now in parentheses 1 minus sine squared x, using Pythagorean identity, right, that becomes cosine squared x divided by the denominator, 1 plus sine squared x squared, and that's cosine cubed x now divided by 1 plus sine squared x squared. Okay, now let's see, cosine cubed, that's as simple as this can get. Let's find the critical numbers now, places where f prime is 0 or f prime does not exist. Now let's look at the denominator. In the denominator, sine is bounded between 1 and negative 1. The fact that you have sine squared, so we know the denominator is always positive, right? And you have a square here on top of that, double squares. So denominator is always positive. Now, is there any way, in other words, there you go, can that be 0? Well, sine squared x is negative 1. When you square the sine, it cannot be 0, so this is impossible. Nothing squared becomes, I'm sorry, not 0, nothing squared becomes negative. So there's no way 1 plus sine squared x can be 0, right? That's impossible. I'm just gonna say cannot happen. Okay, and if it cannot happen, therefore there is no critical number out of this. So we're just going to focus on the numerator being 0, so we're going to let cosine cubed x be 0, which means cosine x must be 0. The zeros of cosine x in general are pi over 2 plus n pi, right, where n is an integer. Now our focus is in 0 to something like some of the zeros, that would be like pi over 2, 3 pi over 2, and so on. But our focus in 0 to 2 pi, remember that we were given that in the beginning, right? There you go, 0 to 2 pi. So in that interval, the only zeros of the numerator of cosine is going to be pi over 2, 3 pi over 2. So let's draw our sine chart for f prime. And f prime is right up here. This is our f prime. Okay, because we're going to pick test points in a moment. Critical points, we said, this is my reference, is 0. It's going to be pi over 2 and 3 pi over 2, and let's say this is 2 pi. Our focus is in 0 to 2 pi. Okay, now at pi over 2 the derivative is 0, right? at pi over 2, so is at 3 pi over 2. So let's pick a number here, such as pi over 4. And we're going to do f prime at pi over 4. Okay, so I'm doing cosine of pi over 4 cubed divided by 1 plus sine pi over 4 squared. Remember, all we want is the sign, whether it's positive or negative. Now, cosine of 45, 1 over root 2 cubed, positive. In the denominator, that's always positive, so we don't even test for the denominator. Therefore, between 0 and pi over 2, the sign of the first derivative is positive. Now, between pi over 2 and 3 pi over 2, that's between 90 and 180, let's choose pi. Okay, now we have cosine of pi cubed over the denominator. Remember, it's always a square, so it's always positive. I don't even test in that. Cosine of pi is -1, -1 cubed. So you have negative over positive. Therefore, f prime will be negative. F prime positive, f prime negative. So transition from positive to negative, that's going to be a local or relative max. Now, beyond 3 pi over 2, let's focus on that one. Beyond that, let me choose, so that we're looking at between 270 and 360 degrees. I'm going to pick, doesn't matter, 7 pi over 4, right? I'm thinking this. 1, 2, 3, 4, 5, 6, 7 pi. Each of these is pi over 4, right? 2, 3, 4, 5, 6, 7 pi over 4. That's what I'm thinking. Special angles. At 7 pi over 4, cosine of 7 pi over 4, because we are in the third quadrant, cosine will be positive. You cube it, it's going to stay positive. Denominator, we said, was always positive, so this will be positive. Notice I'm not using a calculator to actually get these numbers, because that's not what we want to do, right? We just want to look at the sign of the expression. And the derivative is now positive. F prime is positive. Again, the transition from this time at 3 pi over 2, we have transitioned from negative to positive. So at that point, we have a local min, right? We have an L min at this point. And we are good. Now we can actually answer the question for part A, increasing, decreasing. Let's look at interval over which it is increasing and decreasing. So for increasing, it's going to be 0 to pi over 2 and 3 pi over 2 to 2 pi. And it will be decreasing from pi over 2 to 3 pi over 2. Okay. Now, the extrema. Let's go L min and L max. These are relative min, relative max. So we have an L max at pi over 2 and L min at 3 pi over 2. At 3 pi over 2, this happens at pi over 2, correct? Sorry, I don't know what happened here. Sometimes my note just goes berserk. Okay, pi over 2 max, 3 pi over 2 min. Yeah, so just now remember, these are not the values. This is where it happens. So I need to do f at 3 pi over 2 and later f at pi over 2. So when we plug in 3 pi over 2 into sine x over 1 plus sine squared x, we're looking at sine of 3 pi over 2 over 1 plus sine 3 pi over 2 squared. Remember, we're going to the original function. That was sine x over 1 plus sine squared x. Sine of 370 degrees is -1. The denominator is going to be -1 squared. There's 1 on 1 and 2. I get -1/2. That's going to be the minimum. The maximum at pi over 2 is going to be, that's sine of 90 over 1 plus sine of 90 squared. Again, sine of 90 is 1. 1 plus 1 is 2, a half. So these are the values of relative minimum, relative max. So these are, again, the extrema of this function. All right. And I think we're done. We're good with this one. I'm just checking to see everything looks good. Good. Okay. So with that, we're done with section 3.3 and our first derivative test.